So this is where we left off in problem 5. We had taken this object, we had lifted it up at a constant velocity, applying a force that was equal to the weight, so that the net force was 0, so it didn't speed up or slow down. We found the work that we did. At the same time, of course, the force of gravity is acting on the object, just happened to be opposite in direction. So as our force was in line with the motion, angle of 0 degrees, here the force of gravity was opposite to motion, 180 degrees, and since the forces are the same, it did the same amount of work, but it was taking energy away. So we were adding 62 joules in, gravity took 62 joules away. If we look at the equations, we see that the work done by gravity was the negative of the weight times the change in height. There's the weight times the change in height, and the cosine 180 made a negative sign. And as we realize that the mass and the acceleration due to gravity don't change, we just put those inside the parentheses there, and we have this expression, the work done by gravity is the negative change in something, and we gave a name to this. This something is what we call potential energy, where kinetic energy is energy of motion, potential energy is energy of position. So it has nothing to do with whether the object is in motion or not, it just has to do with the position of the object. Or more generally, we'll say, a system of objects have potential energy when they are in a position or location where they don't, quote-unquote, want to be. A system of objects have potential energy when they are in a position or location where they don't want to be. Now, I put want to be in quotes because, of course, we're talking about inanimate objects. They don't really have wants or feelings or desires, but it's actually pretty easy to tell if they're in a position where they don't want to be. So here's a demonstration I would do in class. Let's say there's me, and here's a textbook sitting on my teacher desk or the lab station. And there it is, and it's just sitting there, and if I let go of it, it's just going to sit there. Clearly, the book wants to be there. We would say that there's no potential energy in the system. But if I take that book and move it here at the same vertical height but unsupported and let go, well, clearly it's not going to stay there. It's going to fall. It's going to be in free fall. It's going to fall. It's going to hit the ground. And now it's in a position where it wants to be, but that meant that when it was up here, it didn't want to be there. How do I know? Because I let go and boom, it hits the ground, which means that when it was in this position, it must have had, or the book and the earth together as a system have potential energy. And I know that because if I put it in this location and let go of it, it goes away. So it's real easy to tell if a system has potential energy. If you put it in some place, a position or location where it doesn't want to be, and you let go of it and it goes somewhere else, there must have been some form of potential energy stored in that system. Now here, since I was doing work against gravity to lift it up, this is a gravitational form of potential energy. Throughout the year, we're going to see a number of different types of potential energy, but this is gravitational potential energy. And the equation comes from that little derivation we did there in problem 5. It is mgh. The symbol for potential energy in general is going to be another double letter symbol. It's going to be Pe. The subscript g there indicates this is a gravitational potential energy. So let's go ahead and box it in, new equation. And throughout the year, when we see different types of potential energy, we'll just put a different subscript there on the Pe to indicate what type of potential energy it is. So let's define Pe sub g as gravitational potential energy. You get this potential energy in the system by doing work against gravity. M is mass. We don't need to redefine that. G is acceleration due to gravity. I'm not going to define it here on the slide, but of course, when you list it on your new equations list for the packet, you will of course define every term, whether it's new or old. But H, that's a new term. We haven't officially defined that, so we'll call H height. And what do you suppose height is measured in? Yeah, of course, it's going to be measured in meters. Of course it is. This means we can get the units for gravitational potential energy from the equation. M here is measured in kilograms, and G is measured in meters per second squared, and H now is measured in height. H is measured in meters, so we have kilogram meters squared per second squared. So the kilogram meter squared per second squared is difficult to say, and kilogram meter squared per second squared is difficult to remember, and kilogram meter squared per second squared is difficult to write. Luckily, we've actually already gone through this. We know that a kilogram meter squared per second squared is really the same thing as a joule. We've already proved that for kinetic energy. We don't need to reprove that. So really, all forms of work and energy are in joules. Nice and easy. What do you suppose potential energy is, vector or scalar? Hopefully you guessed scalar. Remember, I've been trying to make this point that a lot of students like this topic because there really are no vectors, at least not yet. Everything's scalar. Work is scalar. All forms of energy are scalar. So potential energy is a scalar as well. Now this becomes rather important because when we get to the value of g, up to this point we had to define a positive direction and talk about whether we're talking about positive g or negative g, positive 9.8 or negative 9.8. Well, now we don't have to worry about that because everything is scalar, which means when you plug in g for this equation, it's going to be the positive value always. No matter what, you will always use positive 9.8 meters per second squared because everything in this topic, up to this point, is scalar. Now, this also means if you're going through a problem and you end up with an unexpected negative sign, and you say to yourself, I'll get rid of the unexpected negative sign by just making it negative 9.8 meters per second squared, well, then you know you're doing something wrong because you should never be using negative 9.8 meters per second squared when involved with energy because everything is scalar. That's an indication that there's something else wrong in the problem somewhere else, and you better find your mistake, because if you don't find it, well, if it's on a test, I will. So we want to make sure you're thinking about that and trying to see why there was this unexpected negative sign. Now, going back to the problem, we saw that the work done by gravity was the negative change in this quantity mgh, and we now define mgh as gravitational potential energy. We can just put that together by saying the work done by gravity is the negative change in gravitational potential energy, and we're going to make that an official new equation. Wg, work done by gravity, is the negative change in gravitational potential energy. A lot of little details in that equation. Make sure you get them all right. All the subscripts, the negative sign, the change, the delta in there, it's all important. We've used this symbol Wg a couple times so far. Let's officially define that as the work done by gravity. So let's think about this idea that says that the work done by gravity always tries to decrease the potential energy in the system. So let's go back to this idea of here I am with the textbook. And let's say I let the textbook go and it falls, boom, hits the ground. And of course along the way, it's acted upon by the force of gravity, which is pointing straight down, and it's moving straight down. So what angle is there between them? Well, that angle is 0 degrees. They're pointing in the same direction. Why is that important? Well, when we think about the work done by the force of gravity, we're thinking about the work equation, F delta x cosine theta, and so now we see the angle between them is 0 degrees, and cosine of 0 is 1, which means that the force of gravity is doing positive work. But now at the same time, it's falling down, it's losing height. So if we think about gravitational potential energy, mgh, if the value of h is decreasing, what's happening to the gravitational potential energy in the system? Sure, it's decreasing. The system is losing gravitational potential energy because the book is getting closer to the ground, closer to where it wants to be. So look what happened. When the work done by gravity is positive, the system loses gravitational potential energy, and that's what the equation says. When the work done by gravity is positive, we have a negative change in gravitational potential energy. The system loses gravitational potential energy. What if instead the book is moving up? So let's say I take the book and I lift it up. So now the book is moving up, but of course the force of gravity is still acting straight down. Now what angle is there between these two? Sure, now the angle is 180 degrees. Everything in terms of work, F delta x cosine theta, cosine of 180 degrees is -1, right? So if it's moving up, the force of gravity is acting against that, we say that the force of gravity is doing negative work. But the object is moving up. So what's happening to the gravitational potential energy in the book-Earth system? Sure, height's increasing. There's an increase in gravitational potential energy. The system is gaining gravitational potential energy. So when the work done by gravity is negative, the system is gaining gravitational potential energy, and that is also shown by this equation. If the system is gaining gravitational potential energy, so delta PEG is positive, but there's this negative sign in it, that means the work done by gravity must be negative. And so it's all right there in this equation. In general, the work done by gravity tends to try to decrease the gravitational potential energy in the system. So continuing in our notes, we've talked about kinetic energy, energy of motion, potential energy, energy of position. We've never actually defined energy, so we should probably do that. We'll have two terms here, energy in general, and then specifically mechanical energy. Now, from previous courses, you probably already have a good sense of what energy is. So if you had to define it in terms of other physics terms and other physical quantities, you might say energy is the, hopefully you said, it's the ability to do work. And if you didn't, well, that is it. That's the definition of energy. It is the ability to do work. So what does that mean? That means that if an object has energy, it can do work on something else. So if you do work on something else, you apply a force through displacement, you give your energy to the other object. And now the other object has energy. So what can it do? it can do work. So maybe it interacts with some other object. It does work on the other object, and it gives up its energy to the other object. Now, the other object has energy. So what does it do? It can do work. And so work, energy, really goes back and forth. They're really, as we say, flip sides of the same coin. The work that you do becomes the energy of another object. Now the other object has energy. It can do work on something else. Back and forth, back and forth. Work becomes energy, becomes work, becomes energy. It's a constant exchange, back and forth, back and forth. Mechanical energy is an umbrella term. It encompasses kinetic energy and all forms of potential energy. It's just the numerical sum of kinetic energy, energy of motion, and all the different types of potential energy. We only have one type right now, but later on in the year, we'll see different types. You put them all together, combine it with kinetic energy, and that's what we call mechanical energy. We often give the symbol E total to mechanical energy, the total kinetic energy and potential energy. And later on in the topic, we'll deal with other types of energy, the non-mechanical forms of energy. But right now, we're just going to deal with mechanical types of energy.